Welcome. We have deployed our applications, but have you ever stopped to wonder how Kubernetes decide which worker node to run specific pod on? That critical decision is made by a core control plane component called Kubernetes Scheduler. The scheduler is like an incredibly smart air traffic controller for your cluster. It look at newly created pod, analyze its requirement, and then evaluate all the available nodes to find the best possible fit. Now the scheduler consider many factors like node affinity roles, taint, toleration. But before the most fundamental understanding of scheduling, you need to master one concept above all others: resource boundaries. Today, we are going to explore how defining CPU and memory requirement for your pods directly influence where and even if they can be scheduled. So let's go to the second slide. The ask resource request. Think about it like this. Before a moving company leads a giant piano onto a truck, they first measure the piano and the truck door to make sure that it will fit. The Kubernetes scheduler does the exact same thing. The pod measurements are its resource requests. A request is amount of CPU and memory that you guarantee your container needs to run. This is the single most important number in the scheduler to look at. It will not even attempt to place a pod on a node unless that node has at least requested amount of resources free. Let's look at the unit. CPU is measured in milli-CPUs or millicores, written as a number with an M. So 500 millicore, it's a half of the CPU core, and 1000 millicore is one full of cores. Memory is measured in bytes, typically using suffixes like MI for memobyte or GI for gigabytes. Let me show you. Here is the difference between the decimal format and binary format. So if I recommend you to use the binary format because this is a consistent way to make sure that you know, because the hardware of machines, like the actual memory size, is in binary format. So it's better to utilize the correct, or let's say binary format, for using and assigning the memory to the pod. But this is only works for memory. It's not the binary format is not working for CPU. So the CPU is in decimal format. So here I have a pod. Let's go to the terminal. Okay. So here I have a pod manifest for application that has two containers, a main node application and a sidecar or front-end application as Nginx. Let me copy paste the manifest. Vim pod YAML. So here is the definition. So now notice how each container has its own resource request block. The scheduler look at the pod as a whole. So it sums the request of all container inside of it. So here we have this request, and then we have this request here. So for our first application, we have 1000 millicore or one CPU, as you can see here, the one without any M next to it, which means that one core CPU, and we have the memory 256 megabyte, and the other one is 64 megabyte. So let's create this pod and see where it's scheduled to place it. This is the interesting part. So let's remove this because I already created. Okay, delete -F. So this will delete the pod. Okay, now let's apply the pod. Okay, it got created. As you can see, the status is pending, which means that we need to describe the pod to see what has happened. Okay, describe pod and then node app. So as you can see, 0 out of 2 nodes are available. One sufficient CPU, one node had untolerated taint. So we will talk about taint and toleration later, but here it says that the controller has enough CPU, but it has taint, which doesn't allow the pod to be running on this node. What does it mean? It means that currently the worker node, which let me describe get node. So we have controller and worker node. If I describe the node, we can see the request, the amount of requests that this current node has. So k describe node, and we can see what amount of CPUs are available. So at the moment, 45% of CPU is claimed. We have pods that have requests and limits on them as on the resources. So they claimed 45% of resources available. So what left is around like 500 millicore, which is right now we are asking for like 1.25 cores. That's why it's not scheduling on this node. So let's change the manifest. Let's delete the pod again, because the pods, unlike the deployment, cannot be changed. The request and limit and this manifestation. The only things that can be changed on the pod is image. That's the difference. So let's remove the pod again, and then changing the CPU and memory limit request. Sorry. Let's say that this is 100 M for 100 millicore, and here is CPU for Nginx is also 100 millicore. And then let's apply this time. Okay. And get the pod. So it's in container creating state, which means that it's already, so to get the pods which and see what node it assigned it to it exactly, we can use the pod OY. As you can see, a node assigned to this pod, the cube worker 01, and it's on the container creating state, which means that it's probably trying to pull the pods from the public repositories. Okay, describe pod and then node app. As you can see, the container frontend and backend both are created and started. So we can see that the pod is running. 2 out of 2 containers are ready. So we can see the logs. logs-f node app. Okay. So default container is backend. So now it's connected to backend, and if anything interesting happens, we can see the logs here. So the scheduler chose the node worker, and as we saw, worker. Okay, now we can see the worker, and then we can describe the worker now after adding. So the numbers should be changed because we added like more CPU to scheduler. So scheduler automatically calculate this measurement and then add it to the node. So okay, describe node. You remember that the value was 45% usage. Now it should be more than that. It should be okay, describe node. Okay, now you can see the CPU usage is 650 millicore, or 65% of our hardware. Look at under the allocatable. So this tells us the total number of resources this pod has available for pod. And down here in the non-terminated pod section, we see our node app. Yeah, here. So it's consuming 1000 it's consuming 200 millicore CPU and 320 megabyte of memory from the node total applicable resources. The scheduler did the math, saw these nodes had enough capacity and made this placement. If no node had this much of capacity, the pod would remain in pending state forever with an event message like insufficient CPU. Okay, so requests are for scheduling, but what happens if a pod is running? What stops a buggy application from using all of the CPUs on the node and starving its neighbors? That's the job of the resource limits. A limit is an absolute maximum amount of resources a container is allowed to use. It's hard ceiling. If a container tries to use more CPU, than its limit, it will be throttled. It means that performance will be artificially slowed down. If a container tries to use more memory than it limits, it's a different story. The process will be terminated with out of memory error or OOM kill. Let's look at another manifest. This time define only limits. Let's demonstrate what happens we reach the maximum limit that we define in a pod definition for a memory. Here I'm going to create a OM demo pod, and here is the YAML definition of the pod. So here the YAML. So I'm using again the same Ubuntu image and the same command slip infinity. Instead, I'm going to use a benchmark tool, stress, to create chunk of memory out of this pod. So I set the memory limitation 100 megabyte. Yeah, and the request is 50 megabyte. Let's save the pod and then apply the manifest. Should be OM YAML. Yep. In order to test, we need to install the main requirement, stress, to claim chunk of memory and see the behavior of our pod and container runtime. Let's see if the pod is running. Yeah, the OM demo is in running state. So let's execute this. This basically update the package repository and then installing the stress application for us from the apt repository. And then after that, we are going to create 200 megabyte instead of 100 megabyte current memory of the pod. Then we are going to run this command, which is stress like 1 and 200 megabyte and VM keep. So as you can see, it immediately killed my session. Like I was running a bash session on the container, and now it's restarted. But this first time, the restart happened by the kernel, Linux kernel. But if I run the same command next again, so because the container restarted, all of my changes disappeared. So I need to install the stress command again, or stress application again. And then run the bash stress again. We can see that this time the status is OM kill, which means that the container runtime this time killed our container. For CPU throttling, it's the same, but instead of killing the container gets slowed down. So if you are doing some arithmetic processes or calculation, the calculation maybe taking more time. It depends on the process. Some processes can tolerate the throttling, but some other can't. So it's different. Let's go back to the slides. Let's talk about the best practices. The best practice is setting both. The golden rule and the clear best practice is to always set both request and limit for every container in production. Request gives your pod guarantee quality of service and ensures that it gets scheduled on the node that can support it. And limits protect the node from resource-hungry application and prevent one noisy neighbor from impacting everyone else. Let's look at the final complete example. So here I'll only print the YAML definition, the part that we have request and limit. So as you can see, we have request some memory and some CPU size like 250 megabyte memory and 1 core CPU, and then the limit is also always higher, like 512 megabyte and 2 CPU core. So this configuration is ideal. It's tell the scheduler the container needs at least 1 CPU core and 250 MI of memory to start. Then it tells the node when it's running, never let this container exceed 2 core and 512 MI of memory. This creates a burstable pod, which is guarantee its request resources, but can burst up to its limits if extra resources happen to be free on the node. If we describe the node running this pod, we will see both request and limit columns are now filled, reflecting our configuration. So let's summarize. The scheduler uses resource request to make a placement decision. It's a guaranteed minimum of your pod's needs. Resource limits are enforced at the runtime to ensure stability and prevent any single pod from consuming all of your node's resources. By setting both, you create a stable, predictable, and well-behaved application. This is the foundation of effective resource management in Kubernetes. In our next topic, we'll look at the tools that we manage this YAML manifest at scale.